9.2 lesson 3, series and converges. 9.2 lesson 3, series and convergence. Objectives. 1. You will understand when the nth term test for divergence can be used to determine whether a series diverges. And 2. You will understand when the nth term test for divergence cannot be used. And I'll tell you right away when it cannot be used. It's called the nth term test for divergence. You can never conclude that a series converges by using the nth term test for divergence. This particular test will only tell you if a series will diverge, never if it will converge. That's why it's called the nth term test for divergence. So vocabulary, the nth term test for divergence. So here we have the limit of the nth term of a convergent series. This is theorem 9.8, and theorem 9.9 is the nth term test for divergence. What is the relationship between theorem 9.8 and theorem 9.9? Let's understand that. Theorem 9.8 is a conditional statement. If P, then Q, or we can write P implies Q. It is a conditional statement. Theorem 9.9 is the contrapositive of this conditional statement. It is not Q implies not P. So let's look at the two theorems. Theorem 9.8 states if you have a series that converges, then the limit of the nth term as n approaches infinity must be 0. Look at theorem 9.9. It states that if the limit of the nth term as n approaches infinity is not equal to 0, so basically it is the negation of the conclusion from theorem 9.8. So you have Q as the conclusion in theorem 9.8, and you have the negation of that, not Q, as the hypothesis in theorem 9.9. So if the limit of the nth term as n approaches infinity is not equal to 0, then our series would diverge, which would be the negation of the hypothesis from theorem 9.8. So we have P implies Q, and in theorem 9.9 we have not Q implies not P. So the relationship between the two theorems is that theorem 9.9 is the contrapositive of theorem 9.8. And in logic, a conditional statement is logically equivalent to its contrapositive. So if one is true, the other has to be true. So the proof of theorem 9.8 is sufficient for us to know that theorem 9.9 must be true, because theorem 9.9 is logically equivalent to theorem 9.8 because it is the contrapositive of it. I can demonstrate this logic with a real-life example. So consider a conditional statement P implies Q. If it is raining, then there are clouds. Now this is a true statement. If it's raining, there has to be clouds because the rain is coming from clouds. So consider the contrapositive of that statement. If there are no clouds, then it is not raining. That's also true. You can't have rain unless you have clouds. So if there are no clouds, then it is not raining. So these are logically equivalent. Now I also want to use this example as an opportunity to show that what we call the converse of a conditional statement is not logically equivalent to the conditional statement. So if I have P implies Q, but if you have Q implies P, that's called the converse. And it is not logically equivalent to the conditional statement. It would read, for our example here, if there are clouds, then it is raining. Obviously, that's not true. We've experienced many cloudy days, but there was no rain. So the point that I want to make is you have a conditional statement. Its converse is not logically equivalent to it. So you could have a true conditional statement, but the converse could be false. However, its contrapositive is logically equivalent. So if you have a true conditional statement, the contrapositive must necessarily be true. And this brings up another point that I want to emphasize. Look at Theorem 9.8. You cannot read the converse to make any conclusion. So if you have, this is the converse of Theorem 9.8. If the limit of a sub n, the nth term in our series, if the limit of a sub n as n approaches infinity is equal to 0, this is not true. This is not true. We cannot conclude this. I want to emphasize that we cannot do this. I'm going to put an X. Then we cannot say that the infinite series must converge. This is wrong. Why not? Why is it wrong? Because it's the converse of this conditional statement, and it does not happen to be correct in this case. There may be some instance, there are many instances in math where the converse of a conditional statement may also be true, but you have to prove that separately. It's not logically equivalent. In this case, it's not true. One is true and the other is false. So you can never look at the nth term test for divergence. If the limit of a sub n as n approaches infinity is not equal to 0, then the series must diverge. However, you can never say if the limit of a sub n as n approaches infinity is equal to 0, you cannot say that the series converges. That's just not valid. So we just looked at objective 2. You will understand when the nth term test for divergence cannot be used. It can never be used to conclude that a series converges. It can only be used to conclude that a series diverges. So you will understand when the nth term test for divergence can be used to determine whether a series diverges. We'll take a look at a couple of examples after looking at the proof of Theorem 9.8. So we'll look at the proof of Theorem 9.8. And by logical equivalence, Theorem 9.9 would also be proved, and then we'll look at a couple of examples for the nth term test for divergence. So here we have Theorem 9.8, limit of the nth term of a convergent series. How do we prove it? So in the proof of a conditional statement, you always start with the hypothesis that is given. And then you reason logically to show that the conclusion must be true, that the conclusion must follow. So we assume, we start with what's given. We assume that we have a series that converges. So we have an infinite series that converges. What does it mean for an infinite series to converge? It means that its sequence of partial sums converges. So this is the nth partial sum. So the limit of the nth partial sum as n approaches infinity exists. This is what it means for a sequence to converge, and we start with that. So we want to reason logically until we arrive at the conclusion. So our reasoning starts here. The nth partial sum it can be rewritten as the n-1th partial sum plus the nth term from our infinite series. So that makes sense. So now we want to do this. We're going to take the limit of the left side of this equation, so the limit of the nth partial sum as n approaches infinity. Now, it really makes no difference. It doesn't make any difference if you're considering the nth partial sum or the n-1th partial sum. If you take the limit of either one of these as n approaches infinity, you'll get the same, because n is going to infinity. So it makes no difference whether you're considering the sum of the first n terms or the sum of the first n-1 terms, which is only missing one term. But when you go to infinity, that doesn't matter. So because we know that the limit of the nth partial sum as n approaches infinity is L, the limit of the n-1th partial sum as n approaches infinity must also be L. So it follows that the limit of the nth partial sum as n approaches infinity is L, which is from our assumption. And of course, we can rewrite the nth partial sum as the n-1th partial sum plus the nth term. So you're just replacing the nth partial sum with that, and you're taking the limit of that as n approaches infinity. And using properties of limits, here you have the limit of a sum. So you have You can rewrite that as a sum of two limits. And we showed earlier that if the limit of the nth partial sum as n approaches infinity is L, the limit of the n minus 1th partial sum as n approaches infinity must also be L. So this is L. And of course, this is the limit of a sub n as n approaches infinity. So what do we have here? What we have here is this. The limit of the nth partial sum as n approaches infinity is equal to L by hypothesis, right? And that's equal to, so we have L is equal to the limit of the nth partial sum as n approaches infinity, which is equal to L plus the limit of the nth term of the series as n approaches infinity. So basically, you can subtract L from each side of the equation, and you get that the limit of a sub n as n approaches infinity must be equal to 0, which implies that the sequence with the nth term a sub n must converge to 0. So that proves that if a series converges, then the limit of its nth term as n approaches infinity is equal to 0, and by logical equivalence, its contrapositive must also be true. We want to conclude this lesson by looking at a couple of examples for our two objectives about using the nth term test for divergence. So for the three series that we're looking at, the question that we have is, does the series converge or does it diverge? So we're going to apply the nth term test for divergence to conclude that the two series for 1 and 2 will diverge. So you look at the nth term of the series, and you look at the limit of the nth term of the series. So for number 1, we have that the limit of 2 to the n as n approaches infinity. We know that as n goes to infinity, 2 to the n will also go to infinity. So this limit is not equal to 0. And the nth term test for divergence states that if the limit of the nth term as n goes to infinity is not equal to 0, then the series diverges. So we may conclude by the nth term test for divergence that this series diverges. Let's take a look at the series for number 2. So we're going to look at the nth term, and we're going to see what happens when we take the limit of the nth term as n approaches infinity. So we take the limit of 5 times n to the third plus 1 over 5 times, not 5, but over 2 times n to the third plus n as n approaches infinity. And what we have here is a rational function where the degree of the numerator is the same as the degree of the denominator. So when you take the limit of this rational function as n goes to infinity, because the degrees of the numerator and the denominators are the same, you look at the quotient of the leading coefficients. So this limit is equal to 5 over 2, which is not equal to 0. And the nth term test for divergence states that if the limit of the nth term as n approaches infinity is not equal to 0, then the series diverges. So we're going to conclude that our series for number 2 it diverges by the nth term test for divergence. But what about number 3? Let's take a look at number 3. For number 3, when you take the limit of the nth term as n approaches infinity, what do you get? Well, you get the limit of 1 over n as n approaches infinity is equal to 0. So what does that mean? We don't know. That's what it means. We cannot reach a conclusion about the convergence or divergence of this particular sequence for number 3 based on this work. We have to do something else. So we just saw an example of a case an instance in which the nth term test for divergence cannot be used, and before that, the first two examples we saw when the nth term test for divergence can be used to determine whether a series diverges. The nth term test for divergence can only be used to determine divergence, never convergence.